Okay, so let me remind you where we stopped last time. So we had GT. This was our current algebra. And this has a grading, Z plus grading. And the rth graded piece is G tensor T power R. Okay. And then we had our enveloping algebra, which had inherited this grading. So if you took elements of this form, for instance, then the grade associated, so xi's are in G. These are just random elements. These are not Chevrolet generators or anything. Then the grade associated to it is R1 plus R2 plus Rk. Okay, so then we were interested in the category G of Z-graded modules. And of course, the grading has to be compatible with the grading on G. So that means that V is equal to direct sum Vs and so on. And G tensor T power R Vs is contained in the process. And we had degree 0 maps. Okay. So there's one construction which I should really do. So if you have V in objects of G, you can define the dual. So you have to be a bit careful in defining the dual representation. So V dagger is going to be in objects of G. And how is it defined? Oh, I forgot. And Vs has to be here. Vs is an integrable G module. So it's a sum of, or locally finite. So it's a sum of finite dimensional G modules. These are all equivalent. Okay, so I want to define the dual representation. So for that, you take, so as a vector space, V dagger is just direct sum S and Z, Vs star, which is just Hom Vs C. These are vector space maps, linear maps. And how is the, what is the grading? You define the rth graded piece of the dual to be V minus R dual. Otherwise, it won't give you a graded representation. Okay? And to define finally xt power k, f will be equal to minus f xt power k v. So if you check that, when you check that this is an action, you will see that if you want it to be in this thing, if f is in VR star, then x tensor t power k, f will actually be in VR minus k star, k minus r star. No. Yeah, I think k minus r star. And that's why you need to put in the minus sign, change the order of the group. So if you want to understand why I take minus r, you actually have to check why it's a Lie algebra map. Okay, so that is the dual operation in this category. The dual of a finite dimension, of a sum of finite dimensional representation is finite dimensional, and so it actually lives in that. Okay, so so then we discussed what the simple objects in G were. Okay, so the simple objects in G, I'm talking tech, are indexed by pairs lambda r, which belong to P plus cross Z. Okay? And the representation V lambda r was defined by taking the sth graded piece to be 0 if s is not equal to r, and it to be v lambda if s is equal to r. And the representation is given by evaluation at t. T equal to 0. Okay.
So if you take all homomorphisms, then would it still be a direct sum of finite dimensional Vs itself is potentially an infinite direct sum of representations, right? So you don't want to put any further.
I don't know how to put any further restriction, but the dual of
Product of
yeah.
Okay. But then you're saying it's also further a direct sum of finite dimensional ones?
I think so.
There we are, so I guess Vs is finite.
Yeah, there.
Because will there be finite dimensional weight spaces at least, so you can take dual like that, or that need not happen?
I don't want to put in any restriction at this point. But the point is my dual, all these things will apply only for representations which have finite dimensional pieces and graded pieces in weight spaces. So eventually you want to do this in the good context, but if I don't allow infinite direct sums, the graded pieces to be infinite dimensional, I have problems with projectives and so on. So, I mean, so I suppose you could say, so yeah, I mean, you're right. There is a problem over here because we have an infinite direct sum. So maybe one wants to say you just take the duals of the direct sum of the duals of those finite dimensional. So you write Vs. Yeah. So Vs is a direct sum of V mu's, direct sum M mu. And then you want to take Vs star to be yeah, you don't want to take direct product, you want to do this. So you want this. Okay. So I'm fudging some things a bit because I'm never actually going to use this in some generality. But if I don't talk in this generality, then I can't talk about other things. So. Yeah. Okay, so these are our simple objects. And what is the dual of this representation? So this restricted dual is, so V lambda r. Dagger is just V minus W naught lambda minus r, where minus W naught, where W naught is in the while group of G and the longest element. Is the longest element. So you have to take the dual of the representation V lambda, which is well known to be V of minus W naught lambda, and I have to change R to minus R. Okay, so that is my dual representation. Okay, so then I was in the process of discussing the projective covers of the simple modules. So how did we define projective covers? So I defined a module P lambda r to be U of GT, tensor over UG, and I can just do V lambda r. Okay. So U of GT is a right module for UG. V lambda r is, of course, a module for UG, and I do this. Okay. So what is the, right. Yes, I have everything I need. So what is the sth graded piece of this module? So the sth graded piece is just you take the S minus rth graded piece over here. Oh, I mean square brackets. tensor with UG V lambda R. So let me make some comments. Each graded piece is obviously a right UG module as well, because when I multiply something over here by this, the grade doesn't change. This lives entirely in grade 0. Right? So this is a right module, and so it's this. So the claim is that dimension of P lambda R S is finite. So this is what I mean when I say every time I actually look at examples, I have finite dimensional graded pieces. So why is this statement true? So claim. So I claim that by the Poincare-Birkhoff-Witt theorem, this is further isomorphic, at least as a vector space, and we'll see even better, to U of G tensor TCT tensor over C V lambda R. Do you agree with that? So how do I apply the Poincare-Birkhoff-Witt theorem here? I take a basis where all the things with 0 grade come before all the other things. Okay? So choose a basis of UGT of the following form. So you take x1 tensor T power R1, xk tensor T power Rk, where maybe you want to assume that R1 greater than or equal to R2 greater than or equal to Rk. Okay. So that means any element in UGT can be written Poincare-Birkhoff is U tensor TCT tensor over UG tensor over C of UG. Right? I pick everything where T occurs with the degree at least 1, and then I have all the things with degree 0. And then when I look at this further tensor product, because I'm tensoring over UG, that slides over and acts on V lambda R. Yeah? Okay. And if you look, what are the graded pieces? Now it's quite obvious, I think, that the graded pieces in U of GT plus are finite dimensional, U of G tensor CT. So let's use the notation G of T plus to be equal to G tensor TCT. Okay. So if you look at U of GT plus, and you look at its S graded piece, this has finite dimensional. Do you agree with that? Because how will I get something in this grade? I have to have R1 plus R2 plus Rk adding up to S, right? And these are all positive, so there are only finitely many ways to add it up to get S. So this is because it's spanned by things of the form x1 tensor T power R1, xk tensor T power Rk, with R1 plus R2 plus Rk equal to S, and each Ri greater than 0. Okay? And so now this proves the claim. The claim implies the claim that the graded pieces are all finite dimensional. Okay? So P lambda R is, of course, a weight module. So P lambda R, we claim, is equal to direct sum P lambda R mu with mu and 8 star. Okay. So how would one prove such a statement? So let's take an element H in H, and let's make it act on some element U tensor V, right? Where U is, let's say, in U of GT, and V is in V lambda R. And in fact, I can take, let's say, V nu, where V nu is in V lambda R. Yeah? Such elements span my vector space, correct? I'm just taking an arbitrary element in the first component, and I'm taking a weight vector in the second component, but they obviously span my whole space. Okay? So how does H act on this? By definition, it acts as HU tensor V nu. Right? Which is the same as which is the same as UH tensor V nu plus H bracket U tensor V nu. Okay. All right, so what is this? This is equal to U tensor H of V nu. Do you agree with that? Because H is an element of my Lie algebra, and I can slide it through the tensor. And this is, at the moment, nothing to be done. Okay. So, now, what can I further say about U? I said that such elements span my enveloping algebra, right, with RK greater than 0. So now I can choose my xi's cleverly, right? I can choose them to be root vectors, right? So I can write U as a typical spanning element. I can write as, let's say, x beta 1 tensor t power r1, x beta s tensor t power rs, right? These elements, again, span my enveloping algebra. Yeah? And if I calculate H bracket U, what do I find? I find that this is actually just equal to beta 1 plus beta 2 plus beta s evaluated at H times U. Right? You do the commutators. And so now I've got my result. So I've got that this is equal to beta H. No. It's equal to nu H. This first term is nu H times U times tensor V nu plus H bracket U, which is beta H times U tensor V nu. So my module P lambda R is spanned by weight vectors, and so I've got that is a direct sum. Okay. I need to prove that this, I'm trying to prove, so this is going towards proving that the module is integrable. Okay. So I've got my weight vectors. Now, I'm going to check. Let me start it for you. So now, oh, actually, I've got all the components that I need. So what have I proved? I've proved that the dimension of UGT plus S minus R is finite dimensional. And I've also essentially proved for you that this is a G module. Right? Why have I proved that? Well, it's a very similar argument. Take an element over here, right? Apply an element x in G to it. Right? How does it act? It acts as xu tensor V plus, by definition, it's just left multiplication, which is the same as U tensor xv plus x bracket U tensor V. Right? So, I flip the order, slide the x past, and then I've got this. Okay? So this means that this again belongs to P lambda Rs. So actually I didn't need to do that calculation, but I think it's illuminating. And so this means this is a G module, it's a finite dimensional G module, therefore it's a sum of irreducible pieces, therefore it's in my category. Okay? So P lambda Rs, so at this point I've proved that so P lambda Rs is a G module, is a finite dimensional G module, and so this proves really that P lambda R is in my objects of G. Okay? And the grade, so I make a comment here that the P lambda r k, the kth graded piece, is non-zero, implies k is greater than or equal to r. Okay. So now in particular P lambda. So now I've proved that P lambda r is in my category G. Because I should really be writing objects over there. Let's prove, so now I want to give generators and relations for P lambda r. Okay. I'm sorry? I do, because it's a sum of finite dimensional graded pieces. Oh, no, I don't mean G hat. I get my notations confused sometimes. But no, it's just G. Okay. It certainly is integrable, but for the current algebra here.
What is integrable?
It's just integrable for the underlying G. Sum of locally finite dimension. Modules for G. Okay.
The weight space, that it has a weight space decomposition from this too, right?
Yeah.
Since each graded piece.
Exactly. Yeah. So you can do it either way. I hadn't prepared my notes carefully enough to see that until I finished the calculation. Yeah. Okay, so let's look at generators and relations for P lambda r. So what is an obvious generator for it? So let's write down P lambda r equal to 1 tensor V lambda r. Okay? So I claim that this obviously generates the module. So this generates P lambda r. Okay? So why is that? Take an element u and ug first to begin with. If you look at up lambda r, it's equal to, by definition, u tensor v lambda r. But since I'm tensoring over ug, this is actually the same as just this. Right? So what this means is that this means that 1 tensor v lambda r belongs to ug of the element 1 tensor v lambda r. Right? V lambda r is the canonical highest weight vector. So our module V lambda, so V lambda r was V lambda, right? It's a highest weight vector. And I'm putting the additional, so V lambda would be the highest weight vector over here. I'm putting the additional index r to keep track of what grade I'm living in. Okay, so V lambda r is, so this element V lambda will correspond to the element V lambda r. If I don't keep track of the grade, then I just run into difficulties because I don't know what grade I'm going. So. Okay, so I've got 1 tensor V lambda r, and then now I take u to be in u of gt plus, and I get everything. Right? And I apply it to u, 1 tensor any element v, and that's equal to u tensor v. V is arbitrary. Okay. So P lambda r is cyclically generated by the element 1 tensor V lambda r. And the defining relations, so claim the defining relations are the obvious ones. So I don't need the rest of this. So n plus on 1 tensor V lambda r equal to 0. H on 1 tensor V lambda r is equal to lambda h of V lambda r. I mean 1 tensor V lambda r. and xi minus raised to lambda hi plus 1. This is the Chevalier generator now. On 1 tensor v lambda r is 0. Okay. So here I would have needed the calculation that I did, in fact, to compute weights. Okay. So these are the obvious relations which v lambda r satisfy, and there are no additional relations, is the claim. Okay. So this claim can be, I'll leave you to check it, to be checked. The way you would check it is you define a module which has these as the defining relations, and then show PBW will tell you that it has to be an isomorphism. Okay, so we've got that. And now it's immediate to show that P is projective. So I'm going to, from now on, just to make my life simple, I'm going to write P lambda r to be the element 1 tensor V lambda r. Okay? So P lambda r is projective in G. So you take two objects in G, take a morphism between them. You have P lambda r over there, and you map down. Yeah. And then you look at the element of this, the image of this, that goes to some element B over here, which will satisfy all the defining relations that this satisfies. Yeah. That means that B generates a finite dimensional module. Okay. Now, in our category, which consists of G semi-simple modules, anything is a direct sum of finite dimensional G modules, this will split. So you have a splitting as G modules. That's Weil's theorem, that any short exact sequence splits. So I'll have a splitting as G modules. So you pick A, then A satisfies all the same. You pick A so that A maps onto B and satisfies the relations. And then you map it down there. And this is well defined because this element is generated by this with those given defining relations. Okay, so B satisfies the relations of P, lambda r, and A can be picked to satisfy them using Weil's theorem. I have a map like this, diagram commutes, it's projective. Is that all right?
You're confused. You're just picking A.
I'm not picking any A. So the point is this map splits. So I'm taking an element, I'm picking what B goes to under that map. Yeah, in particular it's a G module. Yeah, this is a G module morphism. So if you have two modules which are sums of finite dimensional modules and a map between them, then it splits. A surjective map between them, then it splits.
I guess you're also sort of implicitly using the fact that the relations only involve things from G.
Yeah. Yeah, exactly. And that's why this map is well defined, because this, the relations that this satisfies are only the G relations. Exactly. So it's projective. Yeah.
Can I just ask a quick question about the graded piece of P lambda r? So you said that you have this, you can realize it as U of G tensor T CT inverse times tensor of C on P lambda. Now if you take this, the first enveloping algebra part, the T CT inverse. I mean, in effect, what are you doing? Are you taking U of G?
Yeah.
And viewing it as a G module.
Right.
Of course, it's infinite dimensional.
Right.
But then only somehow grading the portions, grading these representations so that you, so it's going to be basic. I mean, U of G splits up what as V lambda direct sum dimension of V lambda, right?
Over the center it does that.
Over G it doesn't do this. I mean, Peter Weil should apply here, so it should be more or less have the same way that the coordinate ring of the group.
No, I don't. I think over the center it breaks up as a direct sum of something like that. I think I'm not. Okay, but anyway, yeah.
Anyway, you have this decomposition
Yeah.
with multiplicity somehow this grading is going to sort of keep track of, is going to sort of put a grading on.
No, the UG doesn't have the grading on UG is 0 for me.
I realize that, but what I want to try to say is that somehow it seems to me that what you're doing is you're taking UG, which is a bunch of representations of G with multiplicities, and then you're tensoring each one of those against your V lambda.
You're thinking.
And then you're collecting only some of them.
Yeah.
And that collection is going to somehow depend on the grading.
No, so you're missing the point. So what you're saying about UG being a direct sum of irreducible representations of G is when you regard UG as a G module for the adjoint representation. Yes. I'm not regarding UG as a module for the adjoint representation. I'm regarding it as a module by right multiplication. So when I regard it as a module for right multiplication, when I tensor over UG, I just slip past it. So that's the whole point. I mean, UG has two kinds of G module structure.
But in the end, you should be able to write down, I mean, what each graded piece, what this G module is.
You mean what U of GT is?
In the end, what P lambda R at grading position S is as a G module.
You should, but what you should be able to do is slightly different from what you can do. I mean, this is not, yeah, so this is one of the could be one of the consequences of this BGG thing that I'm talking about. So what you're asking, so now what you're telling me is you want to take this module, right? This is not a G module in any way by left multiplication or right multiplication, because when I put in an element of G, I go beyond the space, okay? So this is only a G module under the adjoint action. And what you want to know is what is the G module decomposition of this? That's what you're trying to ask. So look, if you look at this, right, this just looks like G tensor TCT. So how are you going to regard this as a G module? It cannot be a G module under left multiplication, because I wouldn't stay in this space. Correct? Because this thing is spanned by things of this form, right? And then if I put something like this, I'm no longer in this space. Yeah? However, this is an ideal in my Lie algebra. So G bracket with GT plus is certainly contained in GT plus. Right? Because if I had positive grade, I stay in positive grade. Therefore, this is a module for G via the adjoint action. You extend this adjoint action. So you make the adjoint act on each of these things by derivation. And so then it's a module for G, and it's certainly a direct sum of finite dimensional G modules. Every graded piece is a direct sum of finite dimensional graded modules. And your question is, do I know their decomposition? And that question is very difficult, so I'll tell you why in a few minutes about SL2, even in SL2, for instance. Okay, so for SL, yeah, it's just a difficult question to answer, because it involves all kinds of amazing tensor products which you can't decompose. So you will see many things. You will, for instance, find things like this. The adjoint representation tensor up with R. These are all non-trivial questions to answer what the multiplicities are in general. So yes, you know what they are in some sense, but you don't know the irreducible components which occur and how often.
You want the plathism, or you want the decomposition of the tensor product of the adjoint with itself.
For instance. There are all kinds of complicated things that can occur. You could have things like this. You could have G tensor T squared. So that sometimes it will be, I don't know how to say this correctly, but sometimes you get symmetric powers, and then you'll be tensoring all kinds of symmetric powers. So it's a highly non-trivial question to write down what the G module decomposition is. So
but can you reduce it to the question of just having to take tensor products of various irreducibles, or is it a higher plathism where you sort of take?
Yeah, it's not a tensor product. It's just not a tensor product of irreducible. So if you look at this, it's equal to, so again, don't hold me too much because I'll make mistakes in doing this, but it's roughly correct. You take SK1G tensor skpg, okay, where p is some non-negative integer, and you need k1 plus k2 plus kp to be S. So you need to take tensor products of symmetric powers. If k is 1, you'll get just g, and then you need to know how these symmetric powers decompose, and it's horrible. But one of the consequences of this BGG, at least for SL2, will be to give you a nice formula which tells you in principle how to calculate this in terms of Koska polynomials. Okay. But it's, yeah. So you can say this much explicitly about that tensor product, and this is Poincare-Birkhoff width, so this is not very deep.
But this doesn't help you get any closer to getting this P lambda R S piece.
Sure. Well, I mean, it tells you that the P lambda, so it tells you that the P lambda R S piece,
Which is the tensor of
exactly, of this whole thing with V lambda. Yeah, but so what? These are unmanageable tensor products in general, right? They're too big. Okay, so where was I? Yeah, I proved that it's a projective object. I've told you defining generators and relations. Okay, so let me define. I want to say one more thing about these P lambda R's. I want to say that P lambda R is indecomposable. And it has a unique irreducible quotient, which is V lambda R. And the reason for this roughly is, let's look at P lambda R, let's look at its lambda weight space, and let's look at the rth graded piece of this module. Okay? This is one-dimensional. Okay? So this lambda graded, I'm not saying this is the highest weight vector. The lambda can occur in many places because the adjoint tensor V lambda will have lambda, for instance. But if I demand that it appear only in grade R, then it's one-dimensional. And so this is enough to see. So if you think about it, how would you prove it? You would write P lambda R as a direct sum of two things. In fact, it's equal to, is spanned by our favorite generator. Okay? And then you would write this as a direct sum of two things. And this P lambda R would have to be in one or the other because it's of dimension 1. Okay? It's like the argument to prove that the Verma module has a unique maximal submodule. So this would prove the same thing. And it's indecomposable. Okay. So conclusion, I've proved the statement that I made last time. P lambda R is the projective cover of V lambda R. But my discussion on duals today, P lambda R dual is going to be an injective module. Once I've proved everything for projective, then I just reverse all my arrows. It's going to be an injective module, and is the injective hull or injective envelope of what? So what I said over here is that P lambda R maps onto V lambda R, right? And now I'm going to dualize. So when I dualize, I have to dualize this module and this module. So it's the injective envelope of V minus W naught lambda minus R. Okay? So the graded pieces of the injective, so I told you what the graded pieces of the projective were. So P lambda R lives in grades bigger than R. Bigger than or equal to R. And so the injective module, I minus W naught lambda, its dual, lives in grades less than or equal to R. Okay. So they kind of live in very different parts of the category. Minus R. No, greater than or equal to minus R, right? R, sorry, less than or equal to minus R. Yeah, can't do arithmetic. So this leads to a very interesting phenomenon when we go to highest weight categories and or when we talk about standard modules and so on. So let me just look at my notes. I think this might be a good place to stop for a few minutes. So the next thing I want to do is to compute a few x, which will take some time. So let's just stop for about 10 minutes, start again at 10:25, and then we'll continue. Okay, so one of the things projective modules are good for is, sorry.
I would like to ask a stupid question.
Okay.
This, I am not able to follow why when you take the dual, the degrees become minus. Can you just quickly show that?
Okay, so let's look at P lambda R, right? So what does this look like? So it has its R graded piece plus the R plus 1th graded piece and so on, right? So when you take its dual, you're going to put dual here, and so on. And how did we declare the grade on the dual?
So that's the part where I have.
So if you take V, V dual is equal to direct sum VR star, right?
Right.
And then I said that the V dual R is equal to V minus R star. Is equal to V minus R star. So why is that? Okay, so let's take an element in here. Okay, where do I want it to belong? Well, this lives in the rth graded piece of this, so I want this to belong in the r plus kth graded piece, right? So I want this to be in V dual r plus k, right? So if I look at xt power kf, and I'm given that f belongs to V dagger r, which is V minus r star, by definition. This is my definition. I'm trying to tell you that I get a graded module. Okay, so let's not do that. So let's do this. Okay? So let's just see where this belongs. That's probably the simplest, right? So now supposing I take an element V, by the definition of dual, this is minus f xt power kv. Okay? So I want, now f will only see this element if this element has grade s. Correct? So this is 0 if xt power kv does not belong to Vs. Right? So that means that V must belong to Vs minus k. And that's why you have to do the shift. That's what I said. You won't see why you do it unless you check.
After adding k, you must land in the requisite place.
Exactly. Therefore,
it's not the product of the outside minus. It's the.
Oh no, it's this grade that comes into play. Okay, so that's why you need to check. Okay. So now, this thing with p lambda r's and I lambda r's is answered, right? Okay. Okay, so the good thing about projective modules is they allow you to compute x if you can write down projective resolutions. Those are very hard, but they're at least good for calculating x1. So my goal is to compute x1 v lambda r v mu s. So I'll start with my projective module. So I have P lambda r to V lambda r. Okay, and sorry. And then I have my kernel. Okay. And let's start computing. Apply HOM. So I'll get 0 to HOM. These are now G HOMs. I won't write that G again, but we'll know that. So V lambda r V mu s to HOM P lambda r V mu s to HOM K V mu s to x1 V lambda r V mu s to 0. This is 0 because I now come, the next term would have been x1 of P lambda r V mu s, but this is projective, so that's 0. Okay, so now let's look at this. So let's consider two cases. So let's assume first that mu s is different from lambda r. Probably infinite, but that I don't know.
You have an example where it's more than one.
Oh yeah, this is not projective.
That's not.
K is not projective. It can be very big. I mean, even conjecturally, it's not known, but maybe it's at least as big as s minus r. I mean, the xn, it's most likely that these x are non-zero for at least s minus r. So, but I don't know. But it's very far from being length 1. Okay, so we're doing the case when mu s is different from lambda r. Well, these are irreducible modules, and these are different, so this HOM is 0. Okay? How can this HOM be, what about this HOM? The element P lambda r has to go to something over here, right? And this is n plus invariant, and there are no other n plus invariant things over there. Okay, so you use projective. This has to go to this has to go to 0. Shall I try and explain this again? So this module is generated by this element P lambda r. Yeah? This element is killed by n plus because it's highest weight. Therefore, it must go, if I have a non-zero map here, it must go to something here which is killed by n plus. But this has a unique thing which is killed by n plus, which lives in mu s. And I'm assuming mu s is different from lambda r. So it couldn't have gone to the correct space. Okay. So this HOM is 0. Right? So this is now 0. And so what I've got then is that this is an isomorphism. So this implies that HOM K V mu s is isomorphic to x1 V lambda r V mu s. Are we agreed with this? This is if lambda r is different from mu s. If lambda r equal to mu s, a much simpler calculation, so I'll leave that as an exercise, but let's just finish this one. So if I want to compute this x1 then, I better understand what this HOM space is. Right? HOM of the kernel. So what is the kernel? So this P lambda r maps to K lambda r, V lambda r to 0. So what is the kernel going to be? This lives entirely in one grade, right? And this lives in many grades beyond r, right? So what is the kernel? I've just got rid of everything of bigger grade. Yeah? So the kernel here is just direct sum s greater than or equal to r plus 1 P lambda r s plus 1 s. Do you agree with that? Because just for grade reasons. Okay. Yeah. So let's try L. Okay. Now, so I have to understand this. P lambda R L is generated for any L, for L greater than or equal to R plus 1, is generated by elements of the form x1 tensor T up to xl tensor T. God. Not xl, so L. X some other thing, xs tensor T, P lambda R, where S plus R equal to L. Oh, I keep using S, not enough letters. So M, where M plus R equal to L plus 1. So what is the difference between this statement and the other statements that I was making? In the other statements, I would have powers of T over here, yeah? And here I'm only taking T. I don't want to take T to any power, right? So how would I prove such a statement? So why do I not care if I have a term like this? So why am I not bothering with a term like this? Is the question I'm trying to answer, right? So what do I know about G? I know G is a simple Lie algebra. That means G is equal to G bracket G, right? So if I have X, I can just write X as summation yi bracket zi. You agree that I can do that, yeah? And then X tensor T squared is just summation yi tensor T bracket with zi tensor T. Do you agree with that? Because I'm taking the commutator in the first place, second place, I get T squared. And then this is clearly a combination of things like this, right? So this is equal to yi tensor T, zi tensor T, minus zi tensor T, yi tensor T. So instead of taking the whole thing, I can just, in fact, say it's spanned. Do you agree with this now? Okay. So, in other words, P lambda, so the kernel is, so this is a complicated way of saying that the kernel is generated by its R plus 1th graded piece. So, so the kernel, K, is generated by the R plus 1th graded piece. Okay. You just, as a UG module, sorry. So it's generated as a UGT module by the R, yeah. So these elements span P lambda R, right? Supposing I have this element. All the others are coming by just applying. This element is certainly in the kernel, and everything else is just coming by applying UGT modules, right? So this lives in the R plus 1th graded piece. What is the R plus 1th graded piece? So P lambda R on R plus 1. Okay, so let's make some deductions from this. What does that tell me over here? So this kernel is generated by its R plus 1th graded piece. So what does it tell me about this home space? What can I conclude about S? If I have a morphism from here to here, the R plus 1th graded piece must go to something non-zero, correct? So that tells me that S must be less than or equal to R plus 1, right? But in fact, I want to claim that it tells me that S must be R plus 1. Because I can go back up. So why? So I want to say this implies, let's write the statement and try to prove it. This implies that Hom K V mu S is 0 if S is not equal to R plus 1. This is because you have to use the fact that it's irreducible. So it immediately tells me that S must be, no, it tells me that that's clear, because this is all living in one grade. So yeah, I don't have any room to play with anything. So the R plus 1th graded piece must go to something non-zero here. But this all lives in grade S. So the only way it can go to something non-zero is if S is R plus 1. Okay? So at least now I've got control of S. Let's now analyze what the R plus 1th graded piece of this is. That's equal to U of GT plus in grade 1 tensor V lambda R. Okay. What is U of GT plus 1? It's just G, if you like, G tensor T, tensor V lambda R. Right? So what does this tell me about this Hom space? So this tells me that this Hom space, so if you think about this a little more, this tells me that this Hom space really has to sit inside Hom G, now these are G module maps, so I'll put that in, G tensor V lambda V mu. Okay? Because this stop piece looks like the adjoint representation tensor V lambda R, if you think about it. All the calculations that I did told you that. So it looks like this. So any map from here to here must have non-zero restriction to this thing. It's a GT module map, so in particular a G module map, and so it lives over here. So the conclusion then, I mean this requires, so then so in fact I claim that these two are the same. So that means if I get anything over here, I can produce an extension. Okay? So the conclusion, I haven't quite finished the proof, but I've sketched most of it for it to be now reasonably plausible to say that V lambda R V mu S is 0 if S not equal to R plus 1, and it's isomorphic to Hom G V lambda Hom G K, no, G tensor V lambda R V mu S. Okay. So given a non-zero extension, I can define a Hom space, and given a Hom space, I can do this. That's what this. So to go from here to here requires a little more work, but yeah.
So will X1 be supported in 1 degree only, or it looks like that's
what do you mean? You mean is
because
this?
Because this Hom that you've written down, right?
Yeah.
More or less this G Hom from.
Exactly.
And will that be supported in 1 degree, or will it?
This?
Yeah. Will that?
Yeah, that's now at this point we've got S equal to R plus 1.
Yeah, everything is on R plus 1.
Exactly.
It's again it's of the same. It's sort of a stock complex.
Yeah. Okay. So this is why I say that if you go to higher x, then so when you're doing x1, you find S minus R to be 1. So if you go to higher x, you expect it to be supported at all x up to S minus R. So as an exercise, one should try and take a non-zero element of this. So actually I'll formulate this exercise because it's a generalization of an exercise that we did. Okay? So if you remember, I constructed this module. I don't know what I called it, but we constructed this module G direct sum C, right? for GT. It was an indecomposable module, and I wrote down very explicit formulae for them. Okay, so it's a non-zero element. This is a non-zero element of x1 in G V theta 0, comma the trivial living in 0, 1 in this new language. So you take the adjoint representation in grade 0 and you take the trivial representation in grade 1. Okay? And what we needed to do that was that you had a map. This was called the killing form. You had a map from G cross G to C, which was xy going to trace add xxy. Okay? So as a check to see if you understand either that construction and how to generalize it, you should do the following exercise. Let F be, or let's call it phi, be an element in Hom G, no, Hom G, G tensor V lambda V mu. Prove that there exists a GT module structure on V lambda direct sum V mu using phi, which makes it a non-split, so which makes it a non-trivial element of the X group. So I'll just take V lambda 0, V mu 1. Okay. And I'll make one more comment, which tells you what. So this kappa is a killing form from G cross G to C. You can also, this is the same as saying that kappa is an element of, you can think of kappa as an element in this space. It defines, it's a symmetric non-degenerate bilinear form, so it defines a copy of the center in G tensor G. So if you think of kappa like this, then you can think of phi in this way. So now you just imitate the construction that I gave you for this. And so that will tell you whether you understood that construction and then how to adapt it to that. And we'll complete the proof that the X is exactly what I claim it is. Okay, so now I've computed X1 as an application of this stuff. Okay. So we've now defined and sort of understood two important families. So we've understood simple objects in G, and we've understood projective objects in G. Mm-hmm.
So there are two issues. I mean, one is the X of the two symbols is itself a current module.
No, it's just a vector space.
It doesn't carry a...
It's an abelian group. Yeah, it's a vector space. Homs don't carry, I mean...
Well, I mean, if you were for... Okay. I realized in general it doesn't, but I thought maybe here it did.
No, it's X1 of G. So you kind of...
Okay, but now in this... So given this phi...
Yeah.
Which lives in X1, and you've created this direct sum with this GT structure.
Yeah.
Just to clarify, is V lambda and V mu, are they both living in the same degree? Or?
No, sorry. So this should be here. V lambda 0, V mu 1.
Right, so V lambda is 0.
This is in grade 0, and this will be in grade 1.
So as long as the grades differ by 1, it doesn't really matter where you put them for this purpose.
Well, you can't have this. No, you can't have this as grade 1 and this as grade 0.
No, I mean, but it could be 0 and 1 could be 1 and 2.
Oh, sure, yeah, R and S, exactly, yeah. It's R and R plus 1. That's why I just put 0 in. So, can I go on? Are there more questions? Okay, so now I'm ready to define a third family of modules. So remember, I'm doing things like BGG, which is from category O, where you have simples, projectives, and Vermas. Okay, so now I want to talk about what the analogs of the Vermas are here. Okay. So when you're doing category O and all kinds of other things, there's always this thing called a truncation functor. Okay? So let's talk. So now, in case we'll have many kinds of truncations, but first let's define the following. So supposing I take mu in P plus, okay, I'm going to define a subcategory G mu. So this is going to be the subcategory, full subcategory of G, consisting of objects, all of whose weights are less than or equal to mu. Okay, so you don't want the weights of your module to become too big. You have a natural truncation functor from G to G mu. Okay. So if you take an object V over here, how will I produce a module in G mu? I'll just get rid of all things with weight bigger than mu. But that's not going to be a GT submodule, so I'll take the GT submodule that it generates. So V going to V mu, upper mu, which was V modulo summation U of GT, take the weight space V nu, and you demand that nu be not less than or equal to mu. So I get rid of anything which is not less than or equal to mu. But I can't just take the sum of those subspaces. That's not a submodule, so I'll take the GT submodule that it generates. Equivalently, this is, in other words, another way of talking about these V mu's is that V mu is the maximal quotient of V that lies in G mu. Okay? So such constructions appear all over the place in representation theory. And of course, it's possible, perfectly possible, that V mu is 0. Okay? I'm not ruling that out at all. So it's certainly not a exact functor or anything like that. Okay, so now I can define my global while module. So it's called the global while module. So the global while module W lambda R will be the following. You take P lambda R and you truncate it at lambda. You get rid of any weight which is not smaller than lambda. Okay. What's an immediate consequence? So let W lambda R be the image of the element P lambda R. Right? We defined this as 1 tensor V lambda. What is an immediate consequence of this definition? So an immediate consequence of it is n plus tensor Ct on W lambda R is 0. We've seen this kind of condition all the time when we were doing finite dimensional modules. Now this is getting forced in this language. Why is this true? Well, what would the weight of something over here be? It would be lambda plus some positive root, which is not less than or equal to lambda. Right? So, okay. So,
I don't see any example where V mu can be non-zero. Can you?
I'm giving you.
I understand. That's why is
Why is W lambda r non-zero? This is because you look at V lambda r. You haven't, let me state one more lemma and then I'll tell you why W lambda r is non-zero.
V lambda r is one.
Oh, that's right. V lambda r has
one
this.
quotient.
That's right.
It's a maximal quotient by construction.
Sure.
And V lambda r is one such quotient. No?
So take P lambda r, here, take P lambda r and you restrict it to lambda, okay? You're asking me why this is non-zero, right? So you have P lambda r to V lambda r, you have this map, you've agreed with this so far. Yeah? All the weights here live below lambda. P lambda r is P lambda r lambda is the maximal quotient, which had that property. So it factorizes. So you're asking why is this true? Why is this definition equivalent to this definition? Here, this is a definition, right? And now you're asking why is this the same as this? So you will agree that this is certainly a quotient that lies in G mu by construction. Supposing, so I'll prove that any quotient that lies in G mu is a further quotient of this. Then this would be maximal, correct? Supposing I had another quotient which lies in G mu. Then this better go to 0. First homomorphism theorem.
Thank you.
Yeah. Okay, so this picture shows you that W lambda r in particular is non-zero. Okay. Once a module has a non-trivial quotient, then obviously the original module couldn't have been 0. Okay. So then, so now I want to give you generators and relations for the global wild module. So lemma. So what this is telling me is that when I truncate, I'm getting a new relation, which I didn't see in P lambda r, right? And I want to say that I don't get any more relations. This is the defining relation, additional relation that gets imposed. So lemma, W lambda r is generated by the element little w lambda r. So I don't want to have to write all the relations of P lambda r, so it satisfies, but maybe, okay. N plus tensor Ct of w lambda r equal to 0. And our other favorite relations, H transforms according to lambda H, and Xi minus raised to lambda Hi plus 1 W lambda R is equal to 0. These are the relations of which were there in the P's already, and now this is just the additional thing that I put in. Okay, so that's W lambda R for you. How would you prove such a lemma? What have I just shown? I've just shown that W lambda R, the element satisfies these relations, right? And for the converse, supposing I had a module with this, then I would have to prove that it's a quotient of W lambda R. So proof exercise. It's not terribly difficult. Okay? It's the same idea over and over again, so I'll skip this proof. Now, what is the difference between, so of course, I should give you some justification for why it's called global and so on. But what is the definition of local? What is it? So what is the difference between this global wild module and what we've been calling local? What is missing in this definition? So for the local wild modules, what did we have? So for the local wild module, you had this condition, of course, but you had one more. You had a relation for the entire loop through the Cartan elements, right? H tensor T power R, and that's missing over here.
So these are the defining relations in this case?
In this case, yeah, is generated with, oh, sorry, I should have said with defining relations.
I'm sorry, I missed something. So what is the extra thing here? It is not for P lambda r.
For P lambda r, it was only n plus,
It was okay.
right? So, and for, so P lambda r had only a relation for n plus and a relation for h, right? The global now gets a relation for n plus tensor, the loops above it as well. And the local has a relation for that as well as a bit for the Cartan. So the graded, so let's write the graded local while modules. Okay, they're further quotients of the global with relation, with the additional relation, defining relation, which says that H tensor T power R, no, S, W lambda R is 0 if S is positive. Usually you wanted it to be a scalar, right? But now I want it to live in a graded category, and so the only graded thing that I can put it to is 0. I can't have a scalar, otherwise it won't be graded. Okay? So this is the definition of the local while module. Okay. So I think I don't have time, and I think anyway it's a bit long already. So let me just state what I want to do next time. So I want to continue. So now I've defined for you 4 families of modules, and now we've understood the irreducibles and the projectives, and we need to understand the global and the local. Okay. So, but next time I want to focus on the local. So I want to give some. Since I've always been saying that local while modules are finite dimensional, for instance, but never actually proved it. So next time I want to give a proof. Proved that we need a name for this local while module, so we'll call it WLOC, lambda R. So next time I want to prove that WLOC lambda R is finite dimensional. At least for, I'll just do it for SL2. And I want to tell you exactly what the dimensions are. So, the reason I want to do this is it will actually make it clear why I spent some time talking about the quantum case. Because the formula for the dimensions, which really, from the construction of the module, you would have no idea of why you get that formula. The motivation came entirely from the quantum case. So I think with that, I'm ready to stop for today. So thank you very much.